Hey guys, tonight we're sinking into the ocean's quiet blizzard, a perpetual snowfall that nobody on the surface ever sees, drifting through miles of water in almost perfect silence. You're floating in the twilight zone right now, that eerie middle layer where sunlight fades to the faintest blue glow, and all around you, tiny particles are falling. Not water, not bubbles, something stranger, the accumulated debris of life itself, tumbling toward the seafloor in slow motion, carrying secrets we've barely begun to decode. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're watching from and what time it is for you right now. I love seeing how far this little corner of the internet reaches. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're suspended in water that's cold enough to sting, dark enough that your eyes keep trying to adjust to nothing. The pressure here would crush a submarine if it weren't built right. But you, tonight at least, you're immune to all that. You're a ghost observer in the deep, and you're watching something that most marine biologists will never witness in person. Marine snow in its natural habitat doing what it does best, which is falling and never quite being understood. Each flake drifting past you is different. Some are barely visible, microscopic clumps of organic matter no bigger than a grain of dust. Others are surprisingly large, puffball aggregates the size of your fist, tumbling lazily through the water column like dandelion seeds through summer air, except it's never summer down here. And these aren't seeds of new life, but rather the packaging of old death, dead plankton, fecal pellets from tiny crustaceans, discarded mucus houses that lavations built and abandoned, fragments of jellyfish bells, the shed, exoskeletons of things with too many legs, all of it clumping together, all of it sinking, all of it part of a system that moves more carbon than all the world's rainforest combined. And we still don't have a complete picture of how it works. That's what gets me about marine snow, and maybe it'll get you too in that pleasant way that unsolved mysteries can settle into your thoughts as you drift towards sleep. We've sent rovers to Mars, we've photographed black holes, we've sequenced the human genome, but this snow, this utterly fundamental process happening in the largest habitat on Earth, remains stubbornly incomplete in our understanding. We know it matters, we know it's happening, we just don't know all the hows and whys, and every time we think we're close, the ocean reminds us that it's been keeping secrets since before our ancestors crawled onto land. You watch a particularly large aggregate drift past your face, close enough that you could reach out and touch it if you were actually here, if this weren't just a thought experiment wrapped in a bedtime story. It's rotating slowly, and in that rotation you can see its structure, not solid, but loosely bound, held together by some combination of sticky organic compounds and sheer statistical luck. It looks fragile. It probably is fragile. And yet it's made it this far down, past the feeding frenzies of the surface waters, past the twilight zone predators, and it's still intact, still falling, still carrying its cargo of carbon toward the deep. Scientists call this the biological pump, which is maybe the least poetic name for something so quietly vital. The basic concept is simple enough. Photosynthetic organisms at the surface absorb carbon dioxide from the atmosphere, then die or get eaten, and their remains sink, taking that carbon with them into the deep ocean where it might stay locked away for centuries. Simple, right? Except it's not simple at all, because every step of that process involves variables we can't quite pin down, rates we can't quite measure, and transformations we can't quite predict. How much of the carbon that enters the surface ocean actually makes it to the deep? We have estimates, sure, but the uncertainty bars on those estimates are embarrassingly wide. Why do some particles sink quickly, while others seem to hover in the water column for weeks? We have theories, but the observations keep contradicting them. What happens to marine snow in that vast middle zone where it's too deep for convenient, sampling but too shallow to ignore? We mostly just guess, and hope our guesses are in the right ballpark, and try not to think too hard about the fact that our climate models depend on those guesses being accurate. You're still sinking, by the way. Not falling exactly because you're weightless in this imaginary dive, but descending steadily alongside the snow, watching it accumulate around you like you're inside a snow globe that someone shook and then forgot about. The darkness is almost complete now. Your eyes have given up trying to adjust. If you were really here, you'd need lights, and those lights would change everything they illuminated, because that's another problem with studying marine snow. The act of observing it often destroys it or changes its behavior in ways that make your observation suspect. But tonight, You don't need lights. Tonight, you can somehow see the snow anyway. Because this is my story and I make the rules, and also because sometimes the best way to understand something is to imagine it perfectly before acknowledging all the ways reality complicates that perfection. The snow continues falling. You continue watching. And somewhere far above you, the ocean's surface glitters with moonlight that will never reach this deep, illuminating nothing. Warming nothing, touching only the uppermost skin of a world that extends downward into cold and pressure and mystery for miles and miles and miles. You reach out in this imagined descent where physical laws bend to narrative convenience, and let one of the larger aggregates settle into your palm. It doesn't feel like much of anything. Certainly not like snow, despite the name that's stuck to it for over a century now. It's more like holding a small cloud made of organic confetti, barely substantial, already starting to dissolve at the edges where your imaginary hand disrupts the delicate bonds holding it together. This is what marine snow actually is, not frozen water, not precipitation, in any traditional sense, but something the ocean invented that just happens to look enough like a blizzard that some 19th century oceanographer decided the metaphor was close enough. The aggregate in your palm is mostly dead things. That sounds grim, but down here, death is just another word for resources. That particle of marine snow might contain fragments of diatoms, microscopic algae with glass shells that lived and died in the sunlit surface waters weeks ago. There might be zooplankton feces in there too, which is exactly what it sounds like. Waste pellets from tiny animals that ate the algae and packaged the indigestible parts into dense little parcels. Fecal pellets sink faster than loose particles, so they're actually crucial to the whole system, which means yes, poop is literally helping to regulate Earth's climate, and no, I don't think we acknowledge that enough in polite society. But there's more in your hand than just death and excrement, I promise. See those delicate strands running through the aggregate? Those might be the remains of a Lavasian's mucus house. Lavasians are bizarre little animals. They look like tadpoles designed by someone who'd never seen a tadpole, just heard one described over a bad phone connection. They build elaborate houses out of mucus, complete with filtration systems that trap food particles, and when the house gets clogged, which happens every few hours, they just abandon it and build a new one. The old house collapses and starts sinking, still sticky enough to capture other particles as it falls, creating a sort of organic net that sweeps through the water column collecting debris. And see that shimmer in the aggregate, that faint iridescence? Could be lipids, fat droplets from decomposing organisms. Could be the mineral frustule of a dead coccolithophore, those tiny algae that armour themselves in calcite plates. Could be something we haven't even identified yet, because here's the thing. Every time scientists look at marine snow with better instruments, they find more complexity than they expected. New compounds, unexpected minerals, proteins folded in ways that don't match the organisms we thought contributed them. It's like looking at a city's garbage and trying to reconstruct everything about how that city functions, except the garbage is alive with bacteria, it's chemically transforming as it falls, and also it might be falling through a dimension we can't properly measure. The aggregate is fragile in your hand, but it survived the journey from surface to here, hundreds of meters, maybe more, which required some kind of structural integrity. The question that keeps oceanographers up at night is, what provides that integrity? What makes particles stick together in the first place? You'd think it would be simple chemistry. Sticky molecules attract, form bonds, create larger structures, but marine snow doesn't read the textbooks. Some particles aggregate readily, while chemically identical particles nearby remain stubbornly separate. Some aggregates hold together through turbulence that should rip them apart. Others fall apart for no apparent reason, in calm water, as if they just decided they'd had enough of being a team. The leading theory involves something called transparent exopolymer particles, or TEP, which is a deeply unsexy name for what amounts to microscopic mucus. Phytoplankton secrete this stuff, bacteria secrete it, even some dissolved organic matter can spontaneously form it under the right conditions. TEP is incredibly sticky, the duct tape of the microscopic world, and it acts like glue for marine snow aggregation. But here's where it gets weird. We can't reliably predict how much TEP will be in any given patch of ocean, or why TEP production rates vary so dramatically between seasons, between regions, between species that are supposed to behave similarly. We know it's important, we just don't know exactly how important, or what controls it, or whether climate change is making more of it or less of it, or just redistributing it in ways our models haven't caught up with yet. You let the aggregate slip from your hand and watch it resume its descent. Now slightly smaller thanks to your interference, still falling, still serving its role in the ocean's great carbon export system, even though we don't fully understand the rules it's playing by. Another flake drifts past. This one's smaller, denser, sinking noticeably faster. Maybe that one's rich in mineral ballast, bits of calcium carbonate or silica that add weight and speed the journey down. Or maybe it's just packed tighter, same ingredients but different architecture, like the difference between a snowball and a handful of loose snow, except we can't always explain what determines which configuration wins, and that's before we even talk about the gelatinous stuff. Jellyfish, salps, pyrosomes, all the translucent drifters that pulse and filter their way through the water column. They contribute to marine snow too, and their contributions are enormous and barely quantified. When a jellyfish dies, it doesn't just sink as one tidy package, it disintegrates. It breaks apart into thousands of mucus-rich fragments, each one a potential seed for aggregation, each one adding a burst of organic matter to the marine snow budget. Some years, jellyfish blooms are so intense that they create what amounts to underwater blizzards, overwhelming the seafloor with more food than the bottom dwellers can possibly process. Other years, barely any jellyfish snow at all. We're learning to predict these blooms, sort of, but we're nowhere close to incorporating their effects into global models of how carbon moves through the ocean. You're surrounded by falling particles now, hundreds visible in your imaginary field of view, thousands more beyond it, millions and billions and trillions extending in every direction through the water column, each one carrying its microscopic cargo toward the abyss, each one a little packet of incomplete information about processes we're still struggling to decode. It's humbling, honestly. We live on an ocean planet. We've been studying these oceans for centuries, and this basic transport system, this fundamental way that the surface communicates with the deep, still holds mysteries that make scientists shake their heads and revise their estimates and publish papers with titles that carefully hedge every claim. The snow keeps falling. You keep watching. And that dissolving feeling at the edge of your consciousness, that's just you getting sleepy, letting the rhythm of descent pull you deeper into both the ocean and the night. You're watching two particles now, nearly identical in size, drifting side by side through the water column, like synchronized swimmers who've lost their sense of choreography. One of them, the one on your left, is holding together beautifully, maintaining its structure as it falls, accumulating even more tiny fragments as it descends. The other one is coming apart at the seams, literally disintegrating before your eyes, shedding pieces that disperse into the surrounding water like a dandelion losing its seeds to an invisible wind. Same depth, same temperature, same water chemistry as far as any instrument could measure. So why is one thriving while the other fails? Welcome to the formation mystery, the part of marine snow science where the equations start looking more like wishful thinking than physics. The sticking problem should be straightforward. You've got organic particles in water. Some of them are sticky. When sticky things collide, they stick. Aggregate forms. Aggregate. Sinks. Simple, right? Except collisions in the ocean don't happen in a predictable way. Because the ocean is never still. There's turbulence at every scale, from millimeter-sized eddies created by swimming plankton to kilometre-wide vortices spinning off major currents. Turbulence brings particles together, which should promote aggregation, but turbulence also tears aggregates apart, which should prevent it. The question is, where's the balance point and why does it keep shifting? Scientists have a term for this, the collision aggregation kernel, which sounds like something from a cyberpunk novel, but is actually just a mathematical description of how often particles bump into each other and what percentage of those bumps result in successful sticking. In theory, you can calculate this kernel based on particle size, water viscosity, turbulence intensity, and the stickiness of the organic matter involved. In practice, the calculated values almost never match the observed aggregation. Rates in actual oceans, and the mismatches can be off by factors of 2, 5, sometimes 10. That's not a rounding error. That's a sign that something fundamental is missing from our understanding. One possibility is that we're underestimating how selective the sticking process is. Not all organic matter is equally sticky, obviously, but it turns out that stickiness might vary in ways that depend on biological history we can't easily track. A diatom that was nutrient-stressed before it died might produce different surface chemistry than a well-fed one. A fecal pellet from a copepod that ate mostly diatoms might have different aggregation properties than one from a copepod that ate dinoflagellates. We know this matters in laboratory experiments, but in the actual ocean, where you can't interview each particle about its life story before it dies, how are you supposed to account for it? Then there's the size problem, which is really several problems wearing a trench coat. Small particles, we're talking micrometers here, smaller than a human hair is thick, those behave according to something called Brownian motion, which is just a fancy way of saying they jitter around randomly because water molecules keep bumping into them. Larger particles don't jitter, they sink according to gravity and fluid dynamics. But marine snow aggregates span this size range, growing from microscopic to macroscopic, which means they transition from one physical regime to another as they form, and our models don't handle that transition gracefully. We have equations for small particles. We have different equations for large particles. The middle ground? That's held together with mathematical duct tape and assumptions that make physicists uncomfortable. Watch that aggregate on your left again, the successful one. It just collided with a smaller particle, and the smaller particle stuck, but you didn't see any obvious adhesive action. No visible mucus strands reaching out, no chemical fireworks, just contact, and suddenly they're one object instead of two. That's because a lot of the stickiness is happening at molecular scales we can't observe directly. Charged regions on protein surfaces, hydrophobic patches that avoid water and therefore cling to each other, polysaccharide chains that tangle like microscopic Velcro. All of this is real, all of it matters, and almost none of it is captured in the models we use to predict marine snow formation, because modelling molecular interactions for trillions of particles across entire ocean basins is computationally somewhere between prohibitively expensive and maybe by the year 3000. And we haven't even touched on the biological wildcards yet. Bacteria, remember those? They're everywhere. Down here, colonizing every aggregate within minutes of its formation, and they're not passive passengers. They're actively producing their own extracellular polymers, changing the surface chemistry of the aggregates they live on, potentially making them stickier or less sticky depending on what metabolic mood the bacteria happen to be in. Some bacteria produce enzymes that break down organic matter, which could weaken aggregate structure. Others produce sticky biofilms that might reinforce it. The net effect? We're honestly not sure. Different research groups have measured different outcomes depending on bacterial communities involved, water conditions, and presumably the phase of the moon, or at least that's what it feels like when you're trying to reconcile contradictory results from different studies. There's also the inconvenient fact that marine snow isn't just forming and sinking in a smooth, continuous process. Aggregates can break apart and reform. A large aggregate might fragment into dozens of smaller ones when it hits a turbulent patch of water, and then those fragments might reaggregate later, or they might not. Some particles might cycle through the aggregation fragmentation process multiple times before they finally make it to the seafloor. This creates a kind of stochastic chaos in the system, randomness layered on top of complexity. And if there's one thing that keeps scientists up at night, it's trying to build predictive models for chaotic systems where the initial conditions are unknowable and the governing equations are incomplete. You're feeling that aggregate in your hand again. Different one this time, freshly formed, still accumulating mass. It's tacky to the touch, slightly slippery, and definitely biological in a way that makes you glad this is just an imaginary dive and you're not actually handling decomposing ocean matter with your bare skin. The structure is loose, porous, mostly water actually. Most marine snow is over 90% water by volume, which raises yet another question. How do these things stay together when they're essentially water-filled nets of organic debris? Surface tension helps probably. Chemical bonds help, definitely. But the exact mechanical properties of marine snow, its tensile strength, its resistance to shear forces, its compressibility, those are measured so rarely and under such artificial conditions that our database of marine snow material properties is laughably small. And here's the kicker. Everything we've just discussed assumes that marine snow formation is primarily a physical and chemical process. But what if biology is actively selecting for certain aggregation patterns? What if organisms have evolved strategies to either promote or prevent their remains from aggregating, depending on what's advantageous for their offspring or their associated bacteria? Evolution is clever like that, finding advantages in places we haven't thought to look, and the ocean has had hundreds of millions of years to optimize these systems in ways that wouldn't occur to a human engineer starting from first principles. The two particles you were watching earlier, one intact, one disintegrating, they've drifted apart now, separated by meters of dark water, each following its own fate toward destinations that might be the same seafloor or might be different depths entirely. You'll never know which. Neither will the scientists tracking marine snow in the real ocean. Not really, not with the precision they'd need to close the loop on all these mysteries. The formation question remains open. The sticking stays partially unexplained, and you keep sinking through a blizzard built on principles we're still learning to read. You pull out an imaginary stopwatch, because why not? You've already got imaginary hands in this imaginary ocean, and you decide to time how long it takes for a single aggregate to fall 10 meters. Should be simple math, right? You know the particle size, roughly. You know the density of seawater at this depth. You know gravity hasn't changed since breakfast. So you run the numbers in your head using Stokes' law, that beautiful 19th century equation that describes how spherical objects sink through viscous fluids, and you confidently predict the particle will take about 40 minutes to fall those 10 meters. You wait, you watch. 32 minutes later, the particle has already dropped past your marker. Your equation was wrong by nearly 20%, which in scientific terms translates to, well, that's embarrassing. Welcome to the sinking speed problem, where the universe consistently refuses to behave like our textbooks insist it should, and marine snow falls either faster or slower than predicted with a consistency that's almost insulting. The core issue is that marine snow isn't spherical. I know, shocking revelation. Irregular clumps of organic debris don't behave like perfect mathematical spheres. But Stokes' law assumes spheres because spheres are easy to model, and once you abandon the sphere assumption, the math gets uglier fast. Real marine snow particles are fractal-ish, porous, irregularly shaped blobs that tumble as they sink, presenting different cross-sections to the water at different moments, creating turbulence in their wake that feeds back into their sinking behavior. Modeling that accurately requires computational fluid dynamics, simulations that can take hours to calculate the trajectory of a single particle, and there are trillions of particles in the ocean, so we're back to making approximations and hoping they're close enough. Porosity is part of the problem too. Remember how marine snow is over 90% water by volume? That water isn't just trapped inside, it flows through the aggregate as it sinks, which changes the effective density in ways that depend on sinking speed, which depends on density, which creates a circular dependency that makes physicists mutter darkly into their coffee. A loosely packed aggregate might have nearly the same density as seawater, meaning it sinks incredibly slowly, like a feather falling through air. But as it sinks, water pressure increases, potentially compressing the aggregate, squeezing out some of that internal water, making it denser, making it sink faster. Or maybe the aggregate picks up more particles as it falls, increasing its mass but also its size, and the relationship between mass and drag gets complicated fast depending on whether size increases faster than mass or vice versa. Then there's ballast, the wild card in the sinking speed deck. Ballast means dense minerals, calcium carbonate shells, silica frustules, even tiny grains of lithogenic dust that blew off deserts and settled into the ocean. Add enough ballast to an aggregate and it'll plummet like a stone, reaching the seafloor in days instead of weeks. But ballast distribution is patchy and unpredictable. Some regions have abundant coccolithophores producing calcite plates, others don't. Some seasons bring more diatoms with their silica shells, others favour soft-bodied flagellates that contribute no minerals at all. Dust deposition from atmosphere varies with wind patterns, droughts and industrial pollution. All of this affects sinking speed, and none of it is captured in simple models that just want to use average values and call it a day. You watch another particle fall past you, this one sinking noticeably faster than the last, even though it looks roughly the same size. Could be denser, could be more streamlined, could be tumbling in a way that reduces drag, could be that small differences in initial conditions, how it formed, what it's made of, what microenvironment it passed through, cascade into large differences in behavior, because the ocean loves chaos theory and regularly demonstrates it in ways that make oceanographers question their career choices. There's also the biological acceleration problem, which sounds like something from a self-help seminar but is actually about zooplankton repackaging marine snow into fast-sinking fecal pellets. When a copepod or a salp eats a bunch of slow-sinking particles and packages them into a dense pellet wrapped in a protective membrane, suddenly that carbon is express shipping to the deep instead of taking the slow boat. This can increase sinking speeds by factors of 10 or more. It's hugely important for carbon export. It's also nearly impossible to predict, because it depends on zooplankton abundance, feeding rates, and gut passage times, which vary with temperature, food availability, predation pressure, and probably zodiac signs for all we can reliably forecast. And just to make things more interesting, some fecal pellets don't make it to the bottom intact. They break apart, either through physical fragmentation or because bacteria decompose the membrane, and suddenly that fast-sinking parcel becomes a cloud of slow-sinking fragments again, and all that express shipping gets downgraded to standard mail. The frequency of pellet breakup? Poorly constrained. The depth at which it happens? Varies. The effect on carbon export? Significant but inadequately quantified. Seeing a pattern here? You've been sinking alongside your particle this whole time, and you've now descended another 100 meters, maybe more. The pressure has increased, the temperature has dropped, the light, what little there was, has faded further toward non-existence, and the particles around you seem to be falling at a dozen different speeds, some racing downward, others barely moving, creating a kind of temporal dispersion where aggregates that formed at the same time and place end up spread across hundreds of meters of depth, because their individual trajectories diverged in ways we can't quite explain. This matters for more than just academic curiosity. Climate models need to know how fast carbon sinks, because the residence time of carbon in the surface ocean versus the deep ocean is crucial for atmospheric CO2 projections. If marine snow sinks faster than we think, more carbon gets sequestered in the deep, which is good for climate mitigation. If it sinks slower, more carbon stays in the surface layer where it can easily exchange with the atmosphere, which is less good. Right now, our best global estimates of marine snow sinking speeds have uncertainty ranges wide enough to drive a research vessel through, and those uncertainties propagate through every climate model that tries to predict ocean carbon uptake over the next century. Some researchers are trying to improve predictions using machine learning, feeding neural networks thousands of observations of particle characteristics and sinking speeds, hoping the algorithms can find patterns that human intuition missed. And honestly, it's working better than traditional approaches, which is either encouraging because we're making progress or depressing because we're essentially admitting we don't understand the underlying physics well enough to model it from first principles. Probably both. Science is often both. Your stopwatch is still running, by the way. That particle you were timing has now fallen 50 meters, and it took roughly 2 hours, which translates to a sinking speed of about 25 meters per day, which is actually pretty typical for mid-sized aggregates in this depth range. But typical doesn't mean predictable. It just means that when you average together thousands of measurements, you get a number that feels reasonable. Individual particles remain stubbornly individualistic, falling at their own speeds for their own reasons, like snowflakes that refuse to acknowledge they're part of a statistical distribution. The math stays broken. The predictions stay approximate. And you keep falling through uncertainty, watching particles outpace or lag behind your expectations with a consistency that's become almost comforting in its unreliability. You're not alone down here. I mean, obviously you're surrounded by particles and the occasional confused fish, but there's something else sharing this space with you, something you can't quite see even with your impossible, night-adapted vision. It's everywhere, stretching through the water column in invisible networks, creating structures and pathways that we only discovered relatively recently and still don't fully understand. You're floating through the mucus highway, an elaborate architecture of mucus webs spun by organisms so small you'd need a microscope to appreciate their engineering genius. And these webs are changing everything about how marine snow moves through the ocean. Let's talk about lavations again, because they're the star architects of this mucus metropolis. These little tadpole-looking creatures, most of them smaller than your fingernail, build houses out of mucus that are marvels of biological engineering. Not simple houses either, these are elaborate. Structures with intake filters, concentration chambers, escape hatches and mesh sizes calibrated to capture specific particle ranges. A lavation sits inside its house, beats its tail to create water flow, and filters food particles from the current. When the filters clog, which happens every few hours, the lavacean abandons the house and starts building a new one. The old house collapses, but it doesn't disappear. It sinks, and as it sinks, it becomes a giant sticky net sweeping through the water column, collecting particles that would otherwise sink separately, aggregating them into larger packages, fundamentally altering the flux of material toward the deep. Here's what we know. Lavacean houses can filter up to 15 litres of water per hour, which is impressive for an animal the size of a lentil. We know they're abundant in surface waters worldwide. We know their discarded houses contribute significantly to marine snow, but here's what we don't know. How long do these houses stay intact as they sink? Some observations suggest they hold together for days, sweeping through hundreds of meters of water column. Others show them fragmenting within hours. The difference matters enormously for carbon export estimates, and we can't reliably predict which outcome happens when. Part of the problem is that mucus is biochemically complex. It's not just one substance, but a cocktail of polysaccharides, proteins, and lipids mixed in ratios that vary by species, by nutritional state, probably by what the larvacean had for breakfast. Some mucus formulations are incredibly robust, maintaining structural integrity even in turbulent water. Others dissolve readily, breaking down when exposed to bacterial enzymes or even just ambient seawater chemistry. We have rough ideas about what makes mucus durable versus fragile, but translating those ideas into predictions about real ocean conditions, that's where things get fuzzy, and larvaceans aren't the only mucus architects down. Here, pteropods, sea butterflies, those delicate snails with translucent wings, they produce mucus feeding webs too, casting out nets of sticky material to trap food particles. Foraminifera spin mucus threads. Some diatoms exude mucus that trails behind them like microscopic contrails. Even bacteria produce extracellular polymers that are essentially mucus by another name. All of this mucus is invisible to the naked eye, invisible to most sensors, invisible to satellites, and yet it's potentially restructuring the entire marine snow distribution in ways we're only beginning to measure. You reach out and imagine you can feel it. The mucus highway, I mean. In reality, you'd never notice it with your fingers. The concentrations are too dilute, the structure's too delicate. But in terms of functional importance, these invisible networks are highways indeed, channeling particles along preferential pathways, creating aggregation hotspots where mucus density is high, maybe even affecting how zooplankton navigate and feed. Some researchers suspect that marine snow doesn't fall randomly, but instead follows invisible mucus corridors, like traffic flowing along established routes rather than spreading evenly across all possible paths. If true, that would completely change how we model vertical flux, because instead of treating marine snow as a uniform rain, we'd need to account for spatial heterogeneity created by biological structures we can barely detect. The temporal dynamics are equally mysterious. Larvacean populations boom and bust with seasonal cycles, responding to phytoplankton availability, temperature changes, and predation pressure. During bloom conditions, when larvaceans are abundant, the ocean might be crisscrossed with mucus houses, creating a period of enhanced aggregation and accelerated carbon export. During bust periods, the mucus highway might shut down, and marine snow reverts to slower, less organized sinking. But we don't have good time series data on mucus house abundance at most ocean locations, so we're inferring these patterns from sparse observations and hoping our inferences aren't wildly off base. There's also the question of how climate change is affecting mucus production. Warmer waters change metabolic rates, potentially making larvaceans build houses more frequently or less efficiently. Ocean acidification might alter the chemistry of mucus itself, potentially making it more or less sticky, more or less durable. We have lab experiments hinting at these effects, but extrapolating from laboratory conditions to entire ocean basins is always dicey. The ocean has a way of surprising us with emergent behaviors that don't show up in controlled experiments. And then there are the salps. Because of course there are. Salps are gelatinous filter feeders that look like transparent barrels with input and output ports, and they produce mucus too. Internal feeding mucus that captures particles inside their barrel-shaped bodies. When a salp eats, it's essentially straining water through a mucus net, and when it defecates, it's packaging captured particles into mucus-bound pellets that sink rapidly. Salp blooms can be enormous. We're talking swarms that cover thousands of square kilometers, and during these blooms, the amount of mucus entering the marine snow system spikes dramatically. But salp populations are notoriously unpredictable, appearing suddenly in response to conditions we don't fully understand, then disappearing just as mysteriously. Modelling their contribution to the mucus highway requires forecasting salp blooms, which is approximately as reliable as forecasting lottery numbers. You're drifting through one of these invisible webs right now, let's say. An abandoned larvacean house, 48 hours into its descent, still mostly intact, its mesh walls collecting particles like a trawl net gliding through the deep. You can almost see it if you squint metaphorically. A ghost structure in the water, held together by molecular forces we can measure in laboratories, but struggle to predict in nature. It's beautiful in its fragility, functional in its dissolution, and fundamentally unknowable in its trajectory from creation to decay. How much of the ocean's carbon flux moves through mucus-mediated pathways versus simple gravitational settling? We have estimates ranging from 10% to over 50%, which is less an estimate and more an admission that we're guessing. How does mucus degradation by bacteria affect aggregate stability? Important question. Incomplete answers. Can we detect mucus structures using existing oceanographic sensors? Not reliably, not yet, maybe not ever, without fundamentally new measurement approaches. The highway stretches in all directions, invisible and vital, connecting surface to deep through routes we've barely mapped. And you're floating through it like a ghost on a road that exists mostly in the negative space between what we know and what we need to learn. You're holding a particle of marine snow in your hand again, and this time you're thinking about what's inside it. Not the biological components, we covered those already, but the carbon atoms themselves, the fundamental currency of life and climate, the reason anyone cares about marine snow in the first place. This particular aggregate contains maybe a few micrograms of carbon, which doesn't sound like much until you remember there are trillions upon trillions of these aggregates sinking through the global ocean right now, collectively transporting gigatons of carbon from atmosphere to abyss. That's the biological pump in action, the ocean's great carbon sequestration system, and here's the uncomfortable truth. We lose track of most of it somewhere between where it starts and where it ends. The surface part we've got down pretty well. Phytoplankton photosynthesize, fixing carbon dioxide from seawater into organic molecules. We can measure that. We have satellites tracking ocean, colour, algorithms estimating primary productivity, models that translate chlorophyll concentrations into carbon fixation rates. The numbers have uncertainties, sure, but they're respectable uncertainties, the kind you can publish in reputable journals without reviewers laughing you out of peer review. Let's say the global ocean fixes about 50 gigatons of carbon per year through photosynthesis. That's our starting point, the carbon entering the system. Now flash forward to the deep ocean, below 1,000 meters or so, where carbon that arrives is effectively sequestered for centuries because the deep ocean mixes with surface waters very slowly. We can measure carbon accumulation rates in deep water. We can track dissolved organic carbon concentrations. We can even sample sediment on the seafloor and see what actually made it all the way down. And when we do all that measuring and tracking and sampling, we find that maybe 5 to 12 gigatons of carbon per year make it to the deep ocean as sinking particles. So somewhere between 40 and 45 gigatons of carbon are getting remineralized, broken back down into dissolved CO2, before they escape the surface layer. That much we understand. It's the middle part that haunts us. That vast twilight zone between sunlit surface and abyssal deep, where carbon undergoes its disappearing act and our instruments struggle to follow the plot. You're in that zone right now, that intermediate depth where most of the action happens and most of our uncertainty lives. Here's what should happen, in theory. Marine snow sinks, bacteria colonize it and eat it, respiring the organic carbon back into dissolved CO2, which then mixes back into the surrounding water. The deeper the snow sinks before being completely consumed, the longer that carbon stays sequestered from the atmosphere. Simple, right? But the actual rates of bacterial consumption, the depths at which different components of marine snow get remineralized, the factors controlling how much makes it through the twilight zone versus getting recycled there, all of that is wrapped in uncertainty thick enough to lose a research career in. Part of the problem is methodological. How do you measure marine snow flux in the middle of the water column? The traditional approach uses sediment traps, basically funnels that sit at fixed depths and collect sinking material over days or weeks. Sounds straightforward, but sediment traps are temperamental instruments that seem designed to teach humility. They collect particles that sink into them, yes, but they also miss particles that sink around them, or collect particles that swim into them. Zooplankton are notorious for this. Or alter the local flow field in ways that bias their collection efficiency. Different trap designs give different results. The same trap at the same location can give wildly different results in different deployments. And comparing trap results from different research groups, that's an exercise in creative interpretation. Some researchers have tried using radionuclides as natural tracers, isotopes like thorium-234 that bind particles and decay at known rates, giving you a kind of timer for how fast particles sink. Clever idea, works reasonably well for the upper ocean, but gets messy in the twilight zone where multiple processes affect thorium distributions, and disentangling them requires assumptions that may or may not be valid. Other approaches use optical sensors to count particles, acoustic sensors to detect aggregates, even underwater cameras that photograph marine snow as it drifts past. Each method has strengths. Each method has biases. None of them give you the complete picture, which means our view of carbon flux through the twilight zone is assembled from partial observations using incompatible techniques, like trying to reconstruct a painting from photographs taken through different colour filters. And then there's spatial heterogeneity, which is a polite way of saying the ocean isn't uniform, and that makes everything harder. Carbon flux varies by orders of magnitude between different ocean regions. Coastal waters rich in nutrients have high productivity and intense flux. Oligotrophic gyres in the middle of ocean basins have low productivity and weak flux. Upwelling zones, eddies, fronts all create localized hotspots or cold spots of flux that satellites miss and ships rarely sample. To get global estimates, we measure flux at a few dozen locations and then extrapolate like crazy, using models that relate flux to surface conditions we can observe from space. But those relationships aren't perfect, and the extrapolation errors compound, and the confidence intervals on global carbon export numbers are embarrassingly wide considering how important those numbers are for climate projections. You watch the aggregate in your hand and wonder how much of its carbon will make it to the deep. 20%, 50%. None at all if bacteria are particularly efficient, and the particle fragments before it escapes the twilight zone, there's no way to know for this particular particle, and while we can make statistical statements about large ensembles of particles, the individual trajectories remain mysteries. Here's something that keeps carbon cycle scientists awake at night. Climate change is warming the surface ocean faster than the deep ocean, which increases stratification, which reduces the mixing of nutrients from deep to surface, which might reduce primary productivity, which might reduce carbon export. But warmer water also speeds up bacterial metabolism, which might increase remineralization rates in the twilight zone, which might reduce the fraction of exported carbon that makes it to the deep. These two effects work in opposite directions, and which one dominates, we're honestly not sure. Different models give different answers. The observations we have are too sparse and too uncertain to definitively resolve the question. There are also feedback loops we're barely beginning to understand. If carbon export decreases, atmospheric CO2 increases, which warms the planet more, which further stratifies the ocean, which further reduces export. But if warming shifts plankton community composition towards species that produce more ballasted particles, export might actually increase in some regions. And if ocean acidification affects the dissolution rates of calcium carbonate, which is a major component of ballast, then the whole ballast-mediated export pathway might shift in ways we haven't predicted. It's not just uncertainty, it's uncertainty about interacting processes with potential for nonlinear feedbacks, which is the kind of situation that makes modelers reach for stronger coffee. You release the particle again and watch it disappear into darkness below you, carrying its carbon load toward an uncertain fate. Somewhere, eventually, bacteria will finish what they started, or the particle will reach the seafloor intact, or it'll fragment and be partially consumed and partially buried and partially dissolved in ways that depend on local conditions we haven't measured and may never measure. The carbon will end up somewhere, dissolved in seawater, locked in sediment, respired back to CO2, but the exact pathways and timescales remain frustratingly opaque. We've sent probes to the outer solar system, we've detected gravitational waves from colliding black holes, but this, tracking carbon through a few hundred meters of water in the largest habitat on our own planet, this remains a work in progress, an incomplete story, a crucial piece of the climate puzzle that's still missing too many edge pieces to see the full picture clearly. You've descended far enough now that the boundary above you, that thin layer where sunlight still penetrates, where photosynthesis still happens, where the ocean is recognizably alive in the way we usually think about life, has faded into memory. You're in the twilight zone proper now, that enormous middle layer of ocean between roughly 200 and 1,000 meters deep. And if there's a place where marine snow gets weird, where our understanding fragments into competing hypotheses and contradictory data, it's here. Welcome to the problem depth, the layer that should be straightforward but stubbornly refuses to cooperate with our models. The twilight zone is massive, by the way. It contains more water than all other ocean layers combined if you think about it volumetrically. It's also absolutely packed with life, more biomass than the surface waters in many regions, dominated by fish and crustaceans and jellies that migrate vertically every day in the largest animal migration on Earth. And all of that life is eating, excreting, dying, transforming marine snow in ways that create what scientists politely call intense biogeochemical processing, and what everyone else might recognize as complete chaos for anyone trying to track particles through it. The light here is almost non-existent, just the faintest traces of downwelling sunlight that wouldn't let you read a book, even if books didn't disintegrate when soaked in seawater. Your eyes, or whatever passes for eyes in this imaginary descent, have long since given up on photons and are running on narrative convenience alone. But for the organisms that actually live here, this dim environment is home, and they've evolved exquisite sensitivity to what little light remains. Bioluminescence is common. Eyes are often huge or conversely absent. Everything is adapted to perpetual twilight, and that adaptation includes some remarkably effective strategies for intercepting marine snow before it escapes to the deep. Here's the problem. We need to know how much marine snow survives transit through the twilight zone, because that determines how much carbon gets sequestered in the deep ocean, which determines how effective the biological pump is at regulating atmospheric CO2. But measuring marine snow flux through the twilight zone is astonishingly difficult, because the zone is too deep for easy surface-based observations, and too shallow to ignore, creating a kind of methodological dead zone where most techniques struggle. Sediment traps, our old unreliable friends, get especially cranky at twilight zone depths. The traps collect material, sure, but they're also sitting in water full of swimming organisms that can actively enter the traps and either consume the collected material or die inside the trap and add biomass that wasn't actually sinking. Some researchers have tried adding poison to the traps to kill swimmers, but then you're collecting poisoned marine snow, which raises questions about whether the poison affects bacterial activity or particle integrity. Other researchers use baffles and grids to exclude swimmers, but those same structures might deflect or destroy fragile aggregates. There's no perfect solution, just a menu of imperfect compromises, and different compromises give different flux estimates. And the spatial sampling problem gets worse here, because you can't observe the twilight zone from satellites, and ships are expensive to operate, and autonomous vehicles have limited battery life. So most of what we know about twilight zone processes comes from a few intensively studied sites that may or may not represent the global ocean. It's like trying to understand human civilization by studying 3 small towns and then extrapolating to the entire planet. You'll get some things right, but you'll also miss entire continents of complexity. The organisms here don't help matters. Remember those vertical migrations I mentioned, every evening as surface light fades, billions of tons of zooplankton and fish swim up from the twilight zone to feed in productive surface waters. Every morning, they swim back down, carrying in their guts and their bodies a significant fraction of the carbon that was fixed at the surface. They're not just intercepting marine snow, they're actively transporting it, turning passive sinking into active transport. And our sediment traps don't catch active transport because fish don't swim into funnels if they can help it. This is called the twilight zone pump, or sometimes the migration pump, and it might move as much carbon as the passive sinking flux, or maybe half as much, or maybe twice as much, depending on which study you read and which assumptions you trust. You watch a school of lanternfish, small, silvery creatures with bioluminescent organs, swim past you in formation, heading upward for their nightly feeding. Each one of those fish will eat a few milligrams of zooplankton tonight, digest it partially, and excrete or respire the rest at depth tomorrow. Multiply that by trillions of individual animals, and you're talking about a significant carbon transport pathway that bypasses the marine snow we've been following. But how do you measure it? You can't put sediment traps in front of swimming fish. You can try to estimate fish biomass and metabolic rates and vertical migration distances, but each of those estimates has error bars, and when you multiply uncertain numbers together, the uncertainty compounds exponentially. Then there's the issue of particle transformation. Marine snow enters the twilight zone as one thing and often exits as something quite different, if it exits at all. Bacteria are more active here than in the cold. High pressure deep, breaking down organic matter, releasing nutrients, transforming complex molecules into simpler ones. Zooplankton graze on aggregates, consuming the parts they want and repackaging the rest into fecal pellets. Fragmentation is common. Turbulence created by swimming animals tears apart aggregates, creating clouds of smaller particles that sink more slowly or perhaps not at all. The net effect is that marine snow isn't a static thing falling unchanged through the water column. It's a dynamic, evolving entity that can gain mass, lose mass, change density, change sinking speed, all while crossing the twilight zone. Our models generally don't capture this dynamism well. Most carbon export models treat marine snow as particles that sink at constant speeds and are consumed at constant rates, which is mathematically convenient but biologically unrealistic. Some newer models include size classes and allow particles to fragment or aggregate, which is better, but even these models use simplified representations of processes that are vastly more complex in reality. We're getting closer to accurate representations, but we're not there yet, not even close. And here's a delightful complication. The twilight zone isn't uniformly distributed across the globe. Its boundaries, both upper and lower, vary with latitude, season, and local ocean conditions. In tropical waters, the upper twilight zone might start at 100 meters. In polar regions with deeper light penetration, it might start at 200 meters or more. The lower boundary is even fuzzier, defined not by light but by water properties that transition gradually from intermediate to deep. This means that when we talk about twilight zone processes, we're actually talking about different depth ranges and different physical conditions in different places, and lumping them all together might obscure important regional variations. You're suspended in the middle of all this complexity, floating in a layer that represents both the largest gap in our understanding and the most crucial piece of the carbon export puzzle. Above you, the sunlit zone is relatively well studied. Below you, the deep ocean is stable and simpler to model. But here, in this twilight realm, where biology is hyperactive and measurements are hardest, and the fate of carbon hangs in the balance, here we're still learning, still revising, still discovering that what we thought we knew was incomplete, or just plain wrong. The twilight zone keeps its secrets well, and you're right in the middle of them, breathing water that doesn't exist, watching processes unfold that we've measured inadequately and modelled approximately, suspended in the gap between what textbooks claim and what the ocean actually does. Temperature is a big deal here because bacterial metabolism is temperature dependent, and the twilight zone spans a huge temperature range, from maybe 20 degrees Celsius at the top in tropical waters to 4 degrees at the bottom, and bacterial activity at 20 degrees is several times faster than at 4 degrees. So marine snow sinking from warm surface waters into cold deep waters is experiencing a constantly shifting bacterial degradation rate, which means simple models that assume constant remineralization rates are fundamentally wrong. Better models include temperature dependence, but even those struggle because bacterial communities might adapt to local temperatures, meaning cold-adapted bacteria at depth might work faster than you'd predict from lab experiments with warm water species. Pressure matters too, though we understand this even less well. Deep ocean bacteria are often piezophilic, pressure-loving, adapted to function optimally at high pressure. But most of our experiments on bacterial degradation of marine snow have been done at atmospheric pressure because running experiments at several hundred atmospheres of pressure requires specialized equipment that most labs don't have. There are hints that pressure affects enzyme activity, membrane fluidity, and metabolic rates in ways that aren't captured by simple temperature corrections, but quantifying those effects for diverse bacterial communities across realistic pressure ranges, that's frontier research that's barely begun. And then there's oxygen, because of course there's oxygen. Bacteria need oxygen to respire organic matter aerobically. And while most of the twilight zone is well oxygenated, there are regions, oxygen minimum zones, where oxygen concentrations drop to nearly zero. In these zones, bacterial communities shift to anaerobic metabolism, using nitrate or sulfate instead of oxygen, and the rates and products of decomposition change completely, marine snow sinking through. Oxygen minimum zones might be degraded much more slowly than in oxygenated waters, or it might be degraded differently, producing different compounds, potentially even producing greenhouse gases like nitrous oxide as metabolic byproducts. We have some observations of this, but the global extent and importance of anaerobic marine snow degradation still being figured out. The bacteria are also producing extracellular enzymes, proteins they excrete into the surrounding water to break down large organic molecules into smaller pieces they can absorb. These enzymes don't stay attached to the bacteria, they diffuse away, creating a kind of enzymatic halo around each aggregate. This means bacteria on one aggregate might benefit from enzymes produced by bacteria on a nearby aggregate, or they might compete for the breakdown products, and the spatial distribution of aggregates affects the efficiency of bacterial processing in ways that are almost never included in models because modelling Diffusion and enzyme kinetics around millions of sinking particles is computationally somewhere beyond nightmare. You're still staring at that bacterial biofilm coating your aggregate, and you notice variation even within this single particle. Some regions look more densely colonized than others. Some areas have visible gaps where bacteria haven't established yet, or where they've already consumed everything edible and moved on. Except bacteria can't move on because they're attached to a sinking particle, so maybe they die or go dormant or switch to a different metabolic strategy. The ecology of particle-attached bacteria is rich and complicated, and we've characterized it mostly from samples collected in bottles and jars after hauling them to the surface, which definitely affects the communities we're studying, but we don't know exactly how much. There's also the question of viral predation, because wherever there are bacteriophages and viruses that infect and kill bacteria. Viral lysis of bacteria on marine snow could release organic matter back into the particulate pool, potentially slowing down the net remineralization, or it could enhance remineralization by breaking open bacterial cells and releasing their contents. The role of viruses in marine snow dynamics is almost completely unstudied, not because it's unimportant, but because studying viruses on tiny sinking particles in the middle of the ocean is technically challenging enough that most researchers choose different questions. And speaking of things we haven't studied enough, what about protists? Single-celled eukaryotes, flagellates, ciliates, and others often graze on bacteria, and they're present on marine snow too, probably consuming bacteria and thereby controlling bacterial population size and community composition. But protist grazing rates on marine snow? Barely measured. The effect of protist predation on carbon remineralization? Mostly inferred from theory rather than observation. The aggregate in front of you is an entire world, a microscopic planet falling through the ocean, hosting communities of organisms that are transforming it from moment to moment, and we can describe the major players and the general processes, but we can't predict the outcome for any specific particle in any specific location with any real confidence. The bacterial hitchhikers are running the show, and we're still trying to read the script they're following, squinting at smudged pages with half the words missing. You've been drifting through relatively normal ocean for a while now. Normal in the sense that it's dark and cold and full of sinking particles, which passes for normal at this depth, but something's changing. The water around you is getting thicker, more viscous somehow, and the marine snow is becoming less like a gentle snowfall and more like a blizzard, dense enough that you can barely see past the immediate swirl of particles surrounding you. You've entered the aftermath of a jellyfish bloom, and the rules you thought you understood about marine snow are temporarily suspended while the ocean deals with this gelatinous invasion. Jellyfish are weird, let's just establish that up front. They're mostly water, like 95% water, held together by a thin matrix of proteins and mucus, drifting through the ocean eating whatever they can catch in their tentacles, reproducing in ways that range from straightforward to absolutely bizarre depending on species, and their populations fluctuate wildly, sometimes reaching bloom densities where you can barely move through the water without bumping into them, other times being nearly absent for years. We don't fully understand what triggers these blooms, which is a problem, because when jellyfish bloom they have outsized effects on marine snow dynamics that cascade through the entire carbon cycle. Here's what happens when a jellyfish dies. It doesn't sink as a single unit the way a fish would. Instead, it sort of falls apart. The delicate tissues begin degrading almost immediately, fragmenting into thousands of mucus-rich pieces that scatter through the water column like confetti made of organic slime. Each fragment is a potential seed for aggregation, sticky enough to capture other particles, dense enough to sink, and collectively representing a sudden massive input of organic carbon to the marine snow budget. A large jellyfish bloom can deposit more organic matter to the seafloor in a few weeks than the normal marine snow flux delivers in an entire year. The species matters, of course, because jellyfish come in spectacular variety. Some have thick gelatinous bells that sink relatively intact. Others are more fragile, essentially dissolving in the water as they die. Some have long tentacles that break off and sink separately. Others have feeding structures that detach and drift. And each species has different biochemical composition, different ratios of protein to carbohydrate, different amounts of structural material versus water, which means different degradation rates and different impacts on bottom communities. We have catalogued maybe a few dozen jellyfish species in enough detail to predict their decomposition behavior, and there are hundreds of gelatinous species in the ocean. So our predictive capacity is, charitably, incomplete. salps complicate things further, because they're gelatinous but not jellyfish. They're actually tunicates, more closely related to vertebrates than to cnidarians, which is a fun fact that doesn't help us predict their ecological impact. Salps form chains sometimes, long colonies of individuals linked together, filtering vast amounts of water as they drift. When conditions are right, salps can bloom explosively, going from undetectable to ocean-dominating in a matter of weeks, and when they die, they rain down as gelatinous snow, creating what some researchers have called salp falls that temporarily bury the seafloor in mucus. The deep-sea organisms that encounter these salp falls are often unprepared for them. They're adapted to a low, steady trickle of food, not a sudden deluge, and the result can be a seafloor ecosystem thrown into temporary chaos while everything tries to eat or process or simply survive the onslaught. You're swimming through the remnants of such an event right now. The water is cloudy with dissolved organic matter, and the marine snow aggregates are larger and stickier than usual, incorporating fragments of jellyfish tissue into their structure. Some of these aggregates are sinking fast. The gelatinous fragments add mass without adding much volume, while others are nearly neutrally buoyant, hovering in the water column as they slowly decompose. The heterogeneity is extreme. Measuring flux through this kind of environment with traditional methods is basically hopeless. Sediment traps would clog, optical sensors would saturate, and any attempt to characterize average particle properties would smooth over variations that span orders of magnitude. The bacterial response to jellyfish blooms is equally dramatic. Gelatinous tissue is biochemically different from phytoplankton. Different proteins, different carbohydrates, different lipids, and bacterial communities shift to accommodate it. Species that are rare in normal marine snow suddenly dominate on jellyfish-derived particles. Enzymes that weren't particularly important become crucial. The entire microbial ecosystem reconfigures itself around this temporary resource pulse, and then reconfigures again when the pulse ends and normal marine snow resumes. We've documented these shifts in a handful of studies, but the global significance of jellyfish-associated bacterial community changes? That's speculative at best. There's also the timing problem. Jellyfish blooms don't follow predictable schedules. They're driven by water temperature, prey availability, oceanographic conditions, and probably lunar cycles and vibes and chaos theory for all we can reliably forecast them. This means that jellyfish-derived marine snow is an episodic, unpredictable input to the carbon cycle. Massive when it happens, negligible when it doesn't. And episodic inputs are exactly the kind of thing that's hardest to incorporate into models that prefer steady-state assumptions and smooth functions. You can't just add a jellyfish term to your carbon export model, because jellyfish aren't a constant background process. They're a disturbance, an event, a pulse that disrupts the system and then fades. Climate change is probably making this worse, or at least different, though the details are murky. Warmer waters favour some jellyfish species and disadvantage others. Ocean stratification might reduce nutrient availability for phytoplankton, but could benefit jellyfish that eat zooplankton. Overfishing removes fish that compete with jellyfish for food, or eat jellyfish polyps, potentially releasing jellyfish populations from predation pressure. There are papers suggesting that jellyfish blooms are becoming more frequent and more intense in some regions, but the historical data on jellyfish abundance is patchy enough that proving long-term trends is difficult. We're not even sure whether more jellyfish blooms would increase or decrease overall carbon export. The blooms create massive pulses, yes, but they might also consume zooplankton that would otherwise produce fecal pellets, potentially reducing non-jellyfish flux. You watch a particularly large jellyfish fragment drift past, maybe 10 centimeters across, ribbons of bell tissue trailing behind it like ghostly tentacles. It's sinking faster than most particles you've seen, which makes sense. It's denser, less porous, more streamlined than the typical fluffy aggregate. In a few days, this fragment might reach the seafloor largely intact, delivering a concentrated package of organic matter to whatever organisms are lucky or unlucky enough to encounter it. Or it might be consumed by midwater predators before it gets that far, or it might fragment further and disperse into a cloud of smaller particles. The uncertainty is built into the system, irreducible, frustrating. The blizzard is starting to thin now as you drift beyond the main deposition zone. The water is clearing, marine snow returning to its normal sparse distribution. But the episode has reminded us, that the ocean isn't a constant, predictable machine. It's a collection of ecosystems and processes that pulse and shift and occasionally explode into blooms that temporarily rewrite the rules. And our understanding, Our models, our predictions, they're built largely on observations of normal conditions, with jellyfish blooms and other extreme events treated as anomalies to be acknowledged in discussion sections, but not fully incorporated into quantitative frameworks. The paradox is that these anomalies might dominate the long-term carbon budget in some regions. If jellyfish blooms deposit more organic matter in a few weeks than steady marine snow delivers in a year, then understanding average conditions becomes less important than understanding the blooms. But blooms are hard to study. They're unpredictable, short-lived, spatially patchy. So we end up knowing more about the boring stuff and less about the dramatic events that might actually matter most. The jellies have had their say. The ocean continues its work, and you sink onward through water that's resumed its usual clarity, carrying with you the knowledge that clarity in the ocean is often an illusion. So you finally arrive at the bottom. Not the dramatic, rocky, vent-scarred bottom you see in documentaries, but the vast, soft, seemingly endless plains of the abyssal seafloor, a realm of perpetual twilight, crushed by pressure, chilled to near freezing. And it is here, in what seems like a food desert of cosmic proportions, that the grand, final transaction of the marine snow economy is supposed to take place. The deep-sea diners have been waiting. The problem is, we don't really understand how the restaurant works. Imagine you're a sea cucumber, a frankly ridiculous-looking creature, like a leathery sentient vacuum cleaner bag plopped on the ooze. Your entire world is the few square inches of mud around you. You have no eyes to see the snowfall coming, no rapid movement to chase it. Your metabolism is slower than a Monday morning, and yet you survive. Your existence is predicated on the faith that snow will land within reach. How do you know? Is it just blind, statistical luck? Or is there a signaling system we're missing? The dinner bell might be a chemical one. As a flake sinks through that final mile of water, it's not inert. It's a leaking, oozing parcel of dissolved organic matter, a faint scent trail of decaying plankton and microbial byproducts. To us it's nothing. To the hypersensitive chemoreceptors on a sea cucumber's skin, or the feathery appendages of a brittle star, it might be a booming dinner gong. They might not smell the flake itself, but the chemical plume it disperses in the near-still bottom currents, orienting themselves into the flow like submarines listening for a signal. We've seen them do this with larger carcasses. A whale fall creates a frenzy detectable for miles. Maybe a single snowflake creates a microscopic version of the same alert, a whisper of food here, rather than a shout. Then there's the competition. This isn't a polite buffet, it's a scramble. When a particularly rich flake, a marine pizza, as some researchers dryly call it, lands, it doesn't just sit there, it's immediately attacked, by bacteria first, replicating at speeds that would be considered frantic anywhere else on Earth, then by tiny crustaceans like copepods and amphipods, the scurrying insects of the deep-sea floor. They tear into it, breaking it apart, redistributing its nutrients in their waste, which then becomes food for something else. A sea urchin might bulldoze its way over, mouth on the bottom, literally hoovering up the flake and the top layer of sediment containing 100 others. It's a chaotic, messy, and incredibly efficient recycling system that happens in slow motion. We can drop cameras and see the aftermath, but capturing the precise moment of arrival, the split-second decisions of who gets what, is like trying to film exactly which pigeon gets the first breadcrumb in a park. The event is too small, too fast, and our presence is too disruptive, and that leads to the central dining mystery. The portion sizes are all wrong. By the time marine snow filters through the thieves' gallery of the twilight zone, only about 1 to 3% of what started at the surface actually makes it to the abyssal plains. It's the nutritional equivalent of a single grain of rice falling from a skyscraper window and landing on your doorstep each day. Yet, down here, there are not just scattered survivors, but entire complex communities. Sea pigs, hagfish, giant isopods, tube worms not tied to vents. The math, on paper, doesn't feed them. So either our measurements of the snow's nutritional quality are wildly off, perhaps it's far richer than we think, or the deep-sea creatures are masters of energy efficiency we can scarcely comprehend, living on metabolic rates that border on suspended animation, waking only for these tiny, precious deliveries, or more likely both. They are living on the edge of physics, and we're trying to balance their budget with an accountant's ledger that's missing half the entries. So you lie there, in your mind's eye as that sea cucumber. You feel not the crush of pressure, but the immense patient silence. You're not waiting in emptiness. You're waiting in a system of faint signals and microscopic windfalls, a lottery where the tickets are scented whispers and the prize is just enough energy to exist for another day, another week, another century. The snow will come. It always has. The how and the precisely when is the ocean's secret, one chewed slowly in the dark. And now, into this ancient, delicate system of whispers and windfalls, we have introduced a new ingredient, a synthetic one. It doesn't decay, it doesn't offer nutrition, but it sinks, and it sticks, and it has become tragically adept at pretending to be part of the cycle. You're no longer just following a flake of aggregated life, you're following a hybrid, a particle of history now woven with strands of our own modern carelessness, microplastic. Think of it not as a bottle or a bag, but as confetti. Trillions upon trillions of microscopic shards, fibres from synthetic clothing, fragments from broken down larger items, worn tyre dust that washed from streets to rivers to sea. They are in every surface sample, from the Arctic to the Antarctic convergence, and they have found the perfect vehicle, marine snow, the same sticky mucus webs, the same gentle electrostatic forces that bind diatoms and fecal pellets together. They also bind these inert alien particles. A microplastic fibre becomes a skeleton for a snowflake. A polystyrene bead gets a coating of microbial slime and suddenly gains biological camouflage. It's a hitchhiker on the highway, only it's not just along for the ride, it's changing the route. This is where the mystery deepens and our understanding evaporates. We know the plastic is there. We can count it under microscopes, a sad, glittering pollution in our samples. But what is it doing? Does a snowflake weighted with plastic sink faster, racing through the twilight zone and delivering its carbon payload and its plastic stowaway to the deep sea floor more efficiently? Or do the plastics alter the buoyancy, making the aggregate more likely to drift, to be intercepted and recycled in the midwaters, keeping the plastic in circulation in the food web for longer? We have competing hypotheses, and very few answers. It's like we've added a new type of sand to an hourglass, and we're not sure if it makes the time run faster or slower, or if it just jams the mechanism entirely. Then there's the dining problem, revisited. That sea cucumber, with its exquisite chemical sensors tuned over millennia to detect the faint signature of a lipid or a protein, can it tell the difference? Or does it ingest the plastic-laden snowflake all the same, filling its gut with indigestible, potentially toxic filler? We've seen plastic in the stomachs of deep-sea amphipods from the Mariana Trench. They are eating it. But is it harming them? Is it simply passing through as a worthless bulk, taking up space that could have been real food, slowly starving them from the inside? Or are the chemical plasticizers, the softening agents, the flame retardants, leaching out and causing subtler neurological or reproductive damage? In the deep sea, where life is already balanced on a knife's edge of energy, a slight disadvantage is a death sentence over geological time. We are running a planet-wide unintentional experiment with an unknown control group. There is no pristine deep sea left to compare it to. The most haunting possibility is that the plastic is becoming more than just a passenger. It's becoming a new habitat. The plastisphere, they call it. A microplastic shard, once colonized by a specific biofilm of bacteria and fungi, might look and feel, to a zooplankton, exactly like any other particle. It enters the food web at the very bottom, mistaken for food, and from there it can climb, from the copepod that ate it, to the lanternfish that ate the copepod, to the squid that ate the lanternfish. It bioaccumulates. It doesn't just sink out of sight and out of mind. It becomes part of the living ocean in the worst way. Our snowstorm is no longer just made of life and death. It's now made of life, death, and the persistent, fragmented ghosts of our convenience. We have changed the very recipe of the deep sea's rain, and we are only now, belatedly, trying to read the new, cryptic instructions. So as you picture that slow, endless fall now, see the glitter. Not the not beautiful, blue bioluminescent glitter, but a dull grey synthetic one. A pollution woven into the fabric of the process itself. The ocean is trying to process it, to incorporate it into its ancient cycles. The terrifying quiet truth is that it might just succeed, creating a new, sadder normal where the snow feeds, but also carries a slow, silent poison into the heart of the last great wilderness. This leads us to the quiet, fundamental crisis at the very heart of our knowledge. Every single thing we think we understand about marine snow its size, its composition, its speed, its very existence, comes to us through a filter, and that filter is by necessity brutally destructive. We are trying to study clouds by catching them with a brick. Think about the methods. The most classic tool is the sediment trap, a kind of underwater rain gauge, a tube or a series of cups on a mooring line, left for months to collect whatever sinks past. It seems elegant, passive, unobtrusive, but you're asking a fragile, loosely bound aggregate of mucus and dead plankton, drifting in a near weightless equilibrium, to suddenly hit a collection surface, be preserved in a poison-like formalin or a zide to stop decay, and then sit for half a year before some graduate student in a lab coat gingerly opens it. What arrives at the surface in that cup is a forensic relic. The architecture is gone. The delicate, porous cathedral has been collapsed into a slurry. The living community of hitchhiking microbes has been fixed, killed, and congealed. It's like trying to understand a snowflake by studying a puddle. Then there's the act of collection itself. The great tool of modern oceanography is the CTD rosette, a metal carousel of large bottles that snap shut at different depths. We lower it, it collects water, and we filter that water to find the suspended particles. But the mere act of lowering a heavy metal frame through the water column creates a bow wave, a pressure wave. Turbulence, it can shear apart the very aggregates we're trying to capture. The larger, more fragile snowflakes, the ones that might be most important for fast carbon transport, are the ones most likely to be disintegrated by our instruments before we even get a chance to see them. We are, in a very literal sense, measuring what survives our measurement. This is the sampling paradox. To know the snow, we must capture it. But to capture it, we must destroy its essence. It's the Heisenberg uncertainty principle played out on a global ecological scale. Our presence alters the state. So we resort to workarounds, each with their own flaws. Underwater cameras and laser-based particle sizers can image snow in situ, without touching it. This is a revelation. We can see size, shape, sometimes even get a fuzzy idea of composition, but a camera can't tell you the chemical makeup. It can't sequence the DNA of the bacteria clinging to it. It can't measure the isotopic signature that tells you where its carbon came from. The non-invasive methods give us shape without substance. The invasive methods give us substance, but of a shape that no longer exists. And then, the scale. The ocean is incomprehensibly vast. A single sediment trap might represent an area the size of a dinner plate. We are extrapolating the behaviour of a planet-wide, atmospheric phenomenon, a snowfall from a few dozen dinner plates scattered randomly across 70% of the Earth's surface. The gaps between our data points are oceanic. A storm could pass one trap and miss another by a kilometre. A swarm of zooplankton could graze a patch of water clean above one trap, leaving the neighbour untouched. The heterogeneity is insane. We are trying to map a blizzard with a handful of thimbles. So we sit with our flawed data, our beautiful, intricate models built on foundations of elegant guesswork. We know the picture is blurry, we know the pieces are missing. The quiet joke in oceanography is that marine snow is what happens between the points where we actually manage to measure something. Our entire science is an act of profound and respectful interpolation, of connecting dots with lines of logic and theory, always aware that the true picture is in the gaps, in the moments we missed, in the snowflakes that dissolved against the side of a sampling bottle before it ever clicked shut. We are blind men describing an elephant, but the elephant is made of mist and it's constantly falling through our fingers. And now the entire system, this delicate, blind man's elephant made of mist, is being placed on a new, warmer stage. The ocean isn't just a container for this process, it's the director, the set designer, and the lead actor. Change its fundamental properties, and you change the story of the snow from the first line. This is where our incomplete knowledge becomes not just academically frustrating, but existentially pivotal. We are trying to predict the plot of a play, while someone is quietly rewriting the script in a language we only half understand. Start with the most straightforward change: temperature. The ocean is warming layer by layer. Warmer water is less viscous, thinner in a fluid dynamic sense. Think of the difference between trying to swim through honey and through warm tea. For a marine snow aggregate, sinking through warmer upper layers might be like falling through a less supportive medium. Does this slow its descent? Perhaps, giving the Twilight Zone thieves more time to pick it apart, reducing the delivery to the deep. But wait, warmer water also holds less oxygen. Expanding low oxygen zones might kill off some of those midwater animals, the very thieves in the gallery. so maybe more snow gets through. It's a climatic tug-of-war with an outcome we can't call. Then, acidification. The ocean is becoming more acidic as it absorbs our excess carbon dioxide. That changing chemistry directly attacks the very building blocks of the snow. A huge component of marine snow is the shells of tiny organisms called coccolithophores and foraminifera, beautiful, intricate structures made of calcium carbonate. In more acidic water, calcium carbonate dissolves. It's like building snowflakes out of salt and then lowering them into a light rain. Those hard mineral shells give aggregates weight, ballast. They are the sinkers. If the shells become thinner, weaker, or fail to form at all, the snowflakes become fluffier, more porous, more liable to drift and be recycled. The fast lane of carbon export, the heavy shell-packed snow, might be closing down, leaving only the slower, less efficient pathways. We might be softening the very bolts that hold the carbon pump together. Now, mix in the changing recipe of life itself. A warmer, more stratified ocean, with a warm, light layer sitting on top of a colder, denser one, is like putting a lid on a pot. It prevents mixing. The nutrients from the deep that fertilize the great phytoplankton blooms in the surface get trapped below the lid. The result? A shift in the type of plankton that can survive. We might see fewer of the large diatom-driven blooms that create massive, fast-sinking snow events, and more of smaller phytoplankton, a kind of permanent, soupy green haze that gets recycled right at the surface. The snowstorm becomes a drizzle, the banquet becomes a meagre snack, and the signal never even makes it out of the kitchen. This is the feedback loop, the true mind-bender. Marine snow is a key lever in the planet's thermostat, shipping carbon away from the atmosphere. But the carbon in the atmosphere is now weakening that very lever. It's a classic negative feedback trying to self-correct, but we may be pushing it so hard it breaks its mechanism. A weaker biological pump means more CO2 stays in the atmosphere, which means more warming and acidification, which further weakens the pump. The numbers on this are the murkiest of all. Our climate models have a parameter for carbon export efficiency. It's a single number, often just guessed at, that represents this entire vast, fragile, misunderstood snowfall. The fate of our long-term climate projections literally hinges on whether we've guessed that number right, and based on everything we've just wandered through, we almost certainly haven't. So you see, the uncertainty isn't a side note, it's the central character. We are watching a slow-motion transformation of the most important precipitation on Earth, armed with a textbook that's missing chapters and a telescope that's slightly out of focus. The ocean is responding, adapting, rewriting its rules in real time, and the gentle, constant snow falling through its heart is both the responder and the response, a trillion-piece puzzle, changing shape as we try to assemble it. So where does this leave us? And more importantly, where does it leave the ocean of 2100 or 2200? We are navigators trying to chart a course through a fog, and our primary compass, our understanding of this fundamental process, is quivering, pointing not to true north, but to a region of probabilities, a cloud of possible futures. Every prediction about the health of the deep sea, the stability of the carbon cycle, the very productivity of our planet, rests on this incomplete foundation. We are building skyscrapers on ground we haven't finished surveying. Imagine you're a climate modeler. Your job is to simulate the entire Earth system, atmosphere, ocean, ice, land, life, in a massive digital twin. You get to the ocean's biological carbon pump. You have to represent trillions of tons of carbon, the chaotic dance of plankton, the complex sticking of mucus, the grazing of unseen swarms, and the slow, fateful fall through 4,000 meters of dark, cold water. You can't possibly. You simulate every snowflake, so you simplify. You create what are essentially mathematical metaphors. If surface productivity is X, then export to the deep is 0.3x. These numbers are called parameterizations. They are our best educated guesses, plugged into the code to make the model run. The unsettling truth is that marine snow science is, in large part, the ongoing effort to get these guesses slightly less wrong. A small tweak to a parameterization can mean the difference between a model predicting a manageable 2 degrees of warming or a catastrophic 3. Our foresight is built on a foundation of elegant estimation. This uncertainty ripples out into every forecast. Will the deep-sea ecosystems of the future be starved? Our answer is a hesitant maybe, in some places depending. Will the ocean's ability to buffer our carbon emissions weaken? Probably, but we're not sure by how much. or when the tipping point might be. Fisheries, which depend on the productivity that is ultimately shunted downward by the snow, could see unpredictable shifts. The very geography of life in the deep, those sea cucumber plains, those coral gardens on seamounts that depend on intercepted snow, could be redrawn over centuries. We are looking at a map where the coastlines themselves might be fuzzy, subject to change. But here's the strangely beautiful part of this predicament. This incompleteness is not a sign of failure. It is the engine of science. The gaps in the map are what call the explorers. The fact that our sediment traps are flawed means we are driven to invent better, gentler eyes. The laser particle counters, the autonomous underwater gliders that can drift for months sniffing out snowfields, the DNA sequences that can reconstruct an entire microbial city from a pinch of degraded sludge. These are all children of our not knowing. Our ignorance is generative. It forces humility, and in that humility, creativity. So the future ocean is not a fixed destination. It is a spectrum of possibilities, a fan of pathways spreading out from this present moment. Down one path, a warmer, more acidic ocean with a shallower, weaker snowfall and a fundamentally altered deep sea. Down another, a resilient system that adapts in ways we haven't imagined, where new types of aggregates form, new players emerge in the planktonic cast, and the pump finds a new, stable rhythm. Our models try to span these possibilities, but they are not oracles. They are tools for understanding the consequences of our guesses. The most honest prediction we can make is this. The marine snow of the future will be different. It will carry a different chemical signature, sink at different speeds, and feed different creatures. The great, gentle blizzard that has fallen for hundreds of millions of years is entering a new chapter. One we're authoring with our emissions, and one we are still struggling to read. Our job now is to refine the translation, to listen more closely to the whispers of the sinking particles, to understand the rules before the game changes beyond recognition. The forecast isn't just about temperature and pH, it's about the fragility and resilience of connection itself, of how life in the sun threads itself into life in the dark, and what happens when that thread begins to fray. And so we arrive here, not at an answer, but at a place. A quiet, accepting space where the unknown isn't a wall, but a horizon. This is the final, gentle truth that marine snow whispers as it spirals into the abyss. That incompleteness is not the temporary state of our knowledge, but perhaps the permanent, beautiful condition of the universe itself. The ocean doesn't owe us a full explanation. It simply is, in all its layered, contradictory, mysterious glory. And our science, at its best, is not a floodlight blaring to reveal every secret, but a soft lantern held at the edge of the dark, comfortable with the vastness it cannot dispel. Think of the snowflake you've been following in your mind all this time. Did it make it to the seafloor as a single entity? Was it torn apart by a tiny translucent shrimp in the twilight zone? Did it dissolve back into its chemical components halfway down, its carbon becoming part of the invisible dissolved ocean soup? The answer is yes, all of the above. Because it wasn't one snowflake, it was every snowflake. Its fate was not a single storyline, but a bell curve of possibilities, a probability cloud of transformation. To demand a single, neat narrative for marine snow is to miss the point entirely. Its essence is its multiplicity, its constant state of becoming something else. Our search for the truth about it was always destined to be a pursuit of shadows. The truth is the process. The truth is the fall. This is what the deep ocean has always taught the restless human mind. Scale matters. Our instinct is to isolate, to categorize, to put a pin through a specimen and label it. But the ocean operates in flows, in gradients, in connections so vast and slow they feel like geology. A snowflake is not a thing, it's an event. A brief congregation of molecules and organisms, a temporary alliance forged by physics and chemistry, lasting just long enough to bridge two worlds. By the time we name it, it's already gone. Our science then becomes not the study of fixed objects, but the study of these fleeting relationships. It is less like stamp collecting, and more like listening to a symphony and trying to understand why a particular combination of notes